Alright, time for another draftphysics.com, debatephysics.com, also video presentation. Yes, still debating momentum versus kinetic energy. And in this video, I'll just go through all the ways you can understand that weight is momentum. And that if you understand that momentum has to be conserved, then you understand that weight has to be conserved. That two things with different momentums can't weigh the same. Okay, they can't move a spring or in some other way you collect the energy, the motion. They, you can't make, I don't know how to just, you could make some analogies between, you can't make 1 pound, okay, dropping 4 feet equal 4 pounds dropping 1 foot. And all of the kinetic energy stuff, obviously, the idea that it takes 25 times the force to move something 5 times as fast, that you have to compress a spring 25 times as much to get 5 times the velocity out of something is nonsense. And clearly, on the other end of that, 5 times the velocity will never do 25 times the work. You'll just do 5 times the work because momentum does all the work. Because momentum was and is and always will be the only thing happening in the universe. It's just masses and velocities, not masses and velocities squared, whatever a squared velocity is. Anyway, as a concept, I mean, mathematics should have some relevance. It's nice to say that you can formalize everything in physics into a mathematical formula, but the formula must have some form that actually relates to physical reality. And so when you say square meter, it makes sense because you can understand it's a spatial dimension and you can make a cube of it. You can't make a cube of velocity. It's not a squareable thing. And so if you're squaring it in some formula and it works, well, it works because you've really misidentified the truth and you're just using some other backdoor way, and it doesn't make any difference in some circumstance that you've misidentified which one is doing which. So this sort of relates to the scale. So we'll start off with that. And what happens in gravity. Because you think, okay, that the thing pushes the scale down, but it's really the Earth pushing the scale up. Everything's always got some little trick to it. All right, you have to look and think. Now, this would all be so nice if physics in the last 350 years had actually taken a spring and compressed it and then launched something and then compress it twice as much and then launch something and 3 times as much and launch. If we had these basic experiments done somewhere, but they haven't been done, and they certainly haven't been done well. Let's certainly put that in quotes, a credible experiment. So you do lots of experiments with things that have variables, like carts with little metal wheels and other kinds of crud. Okay, and and then they don't apply any kind of logic and reasoning to analyzing the variables in an experiment. So back in the 1700s, they would do experiments proving kinetic energy that were certainly flawed in terms of the reasoning and logic behind them. It just wasn't reasonable, the expectation that this is a way of collecting energy. So they would dent clay with round objects. And round objects are basically an object who's changing its shape the deeper it penetrates. So the more it penetrates, the different the shape is that's actually penetrating. So it's as illogical as saying something has more energy because I put a point on it. So if I point an arrow, it'll penetrate further. If I don't point an arrow, it doesn't penetrate as far. Does that mean the arrows don't have the same energy? Of course not. So it's that bad, really. The physics is that bad. All right. So it's probably enough of a preamble. All right, so let's start with the simplest description of weight. So you put something on a scale, okay, and it weighs something. The spring deflects because there's somehow a differential between the object being pushed by gravity and the scale. and the two aren't matching, and therefore you get this deflection or measurement in the spring of the imbalance that exists. And this weight is just the same thing. If I turn the scale sideways, I can also measure impulses. I could measure constant forces. So if I put the scale, if I tied it with some strings, okay, and had it in a river, flowing, I could measure the pressure of the stream. Or I could put it in a wind tunnel. I could measure the pressure of the wind. Now, gravity is different in the sense that gravity doesn't bounce off things and, create the same ability to measure the raw force. So where I might be able to measure the wind fairly accurately, depending on how big, right? If I make the wind catcher, the bigger I make it, the more force I'll put into the deflection of the spring, and the smaller it is, the less force I'll catch. So it has variables that you're not going to have in gravity. But nonetheless, you're catching a force. You're being able to see it in a differential created in the spring. All right, so the basic idea is you put an object on a scale, and what really happens is that, yes, there is 9.8 meters per second of force pushing on the mass, and yet, because of the spring, it's adding, there's something extra. And so the point would be is that it's because the ground is pushing it back with 10.25. The differential is 0.44 meters per second is the argument. Now that might be off, might be off a little bit. But the point being is that there's a definite differential between the two forces. The ground is pushing up with a little more force than the object is pushing down. Now, you could understand why that would happen is if I had a pressurized vessel and it had 9.8 of pressure in it, and then I push new stuff in, new mass into that pressure, you'd understand that now the vessel has to have a higher pressure because I've pushed something into it, some extra. So now, if it was heat, I'm going to make it hotter. I'm adding more pressure, and basically when something's pushing on the earth, it's adding pressure, and the added pressure is this reflection. And so this is true whether there's an elephant on the scale, doesn't matter what's on the scale, it's the same increase in the pressure from the earth, and the pressure in the earth is basically the differential in the two forces that you'd measure in units per second. And so this comes out to be 1 mile an hour. So basically, there's 1 mile an hour of extra force pushing up from the earth, and that's what the spring is acknowledging, that by pushing into the earth, you increase the pressure on the surface of the earth, and the surface is pushing back with the added pressure. Kind of that simple. And so the simple argument is if I did turn the scale sideways and I was to leave it as it was compressed, what it's reading on the scale, which will be the 9, which would be its weight, its mass, because we've just established that this ratio is what we're going to apply to anything to define its weight. And so the real ratio is this 1 mile an hour applied to any mass will compress a spring the same amount as its gravitational weight. So if I push a mouse into a scale sideways at 1 mile an hour, it will weigh mouse. And if I push an elephant at 1 mile an hour, it will measure an elephant's amount of pressure on the spring. And so it makes perfectly good sense. It's a reasonable definition, and it's basically a simple proof that the force is momentum. Whether it's gravity or anything else, it's always just momentum. Now the catch with gravity is I can push something, give it a velocity, and it doesn't have a constant velocity, so it'll be an impulse. But it's still a force, so the force gets used up, compresses the spring expands again. Where you can have a continuous, constant force, which gravity is, and then you have a constant force pushing back up. but it still just depends on the force, period, and it's really all measurable in some idea of a net force, the net product. Okay. So, first example. I probably should emphasize the point. The point is that you can perfectly mimic what the scale is doing by creating a constant motion or a constant pressure or an impulse. So I can take an object and move it at this 0.44 meters per second or 1 mile an hour and create exactly the same spring deflection that happens when you're sitting in gravity, not moving. Yeah, it looks like you're not moving. But what the gravity's kind of telling you is that, yes, you're in a differential of force, and that's what's showing up on the spring, is that this pushing down happens first, and then the earth pushes you back up. And that difference between you having the first push is what essentially the scale is showing. So in fact, there's a little bit more of you going down than there is up. And that's what's pushing on the spring, is that differential. But again, it's more accurate to say it's the differential in the ground. The ground's pushing up a little more than you're pushing in. And it keeps restoring you to a position. Yeah. Well, the point is that this will look exactly like this. There is a speed. You could just imagine a constant force I could apply to something, giving it a constant velocity, and it will hit the scale and read the same thing it would read in gravity. Probably enough. All right, another way to measure weight is to use a gravity balance, a lever, suspended from above the masses. Well, the plane of the lever, let's just say, ideally, because then it will oscillate and tell you exactly how much your weights are off. So I can put a weight on the lever at a distance. I could see if something else weighs exactly the same by measuring the same distance from the fulcrum. And once I get the two objects to be perpendicular, that means I have achieved creating the same on both sides of the lever. I have the same mass. And then I can go 2 units of distance and I can put a half mass out there and that will balance. That's the law of the lever. So by that simple geometry. And the way to really understand what's actually happening is that these masses have to move to balance. Okay, if they're in balance, they move. To get into balance, they have to move. And they're moving by this simple principle that you can have a big M and a small v on one side and a bigger V, a smaller M and a bigger V on the other side. And as long as that total momentum is the same, it will work just fine. It's kind of irritating. I don't know, I gotta find a better lighting system. Anyway, and so that's all you're doing in all of these circumstances. So I'd argue that 350 years ago, everybody believed, in a sense, all the smart people basically understood this kind of principle and that it was basically conserved, that the universe was a machine, was Descartes' basic statement, and it didn't need to be fueled because this motion just kept moving from place to place, and all it was doing is going from being small m's and big v's and turning into a bunch of 5 or 6 you could have lots of different arrangements where yes, you have more small m's and they all have a smaller v, and when you add it all up it's the same mv. So it would just be that no matter where it is, it's just mv. You're just looking for where the mv is gone. Now what fooled them a little bit was the idea of heat. It took a little while to figure out that temperature, the motion in the ground, the motion in an object, temperature was actually just stuff vibrating and moving, and that was also just mv. So anytime you were creating heat, you would obviously have to account for some of your momentum being lost, and that you would have less of it going where you wanted it to go if you were making heat. The less heat you could make, then the more you would conserve the MV. You wouldn't waste it. So anytime something moves across friction, there isn't a force of friction that's consuming anything or causing anything. The simple truth is you're just leaking your MV. So you have an MV, you make contact with other material objects, you give them your MV, and as they start moving, you stop moving. I mean, that's the simple principle. You start, they stop. you stop, they start. It's all just a transfer, and that's all you can do is transfer the MV. You can never have a circumstance where you put a small M and a small V in, and you get a big M out and a big V out. You can't make free momentum, and you can't destroy the momentum. It's always got to be somewhere in the system. So again, those were the conservation laws 350 years ago, and then on one wrong, bad occasion, over a 100-year period, they decided, without any good evidence, because we still don't have any good evidence now, so they certainly didn't have it 300 years ago, because we don't have it now, that they would invent some notion that there's some other quality here, that somehow light things going fast have more energy than heavy things going slow. And they don't. They just have more ability to break things. So all material substances, complicated things, have structure, and you can hit them with a lot of energy in a small location and break their structure, fracture them. It doesn't mean you had more energy. It just means you applied it in a way they couldn't handle, that they couldn't recover from the impact. And that's all it really comes down to. So we're really just back to pointy arrow versus dull arrow, and just making the logical statement that you can't be fooled because your pointy arrow goes deeper. It doesn't mean it has any more energy. It doesn't mean it has any more motion. It doesn't mean it has any more momentum. It just means that you applied it in a way the surface couldn't handle. All right, the structure couldn't handle. All right, so I guess I should emphasize. So this is another object. Doesn't store energy, but I mean you can certainly see the energy, and obviously it's just about the motion. So the lever basically tells you what equals what, and it tells you every single time that momentums equal each other. It doesn't think this has, because this is a half mass going twice the velocity, it doesn't, and that's exactly what it is. So let's just understand that's the explicit real function of the lever, is this moves 1 unit of distance in the same unit of time that this moves 2 units of distance. So it's twice the velocity. So you have a half mass at twice the velocity, and that equals the full mass at 1 velocity. And you can keep extending that as far as you want, and it'll always be true. And what will be true is that you can put force in this side, or you can put force in this side, and it's not going to matter. It's going to oscillate the same with the same force put in. This doesn't take more work to happen than this takes to happen. The work is the equal. The lever is merely switching the mass from one side to the other, a little tiny bit of mass, and that's what the oscillating is made out of as a functional fact. But the explicit truth is it's just a velocity measurer. It's just measuring 2 different velocities and applied to a mass. And so obviously you can create balances where your whole units of energy even, and you'll get it to rebalance with very different masses at different velocities. But it's always momentum. It never, again, this has, by kinetic energy theory, this has twice the energy. Okay, that's what their statement is. Somehow this object, this side of the lever, can do twice the work that this side of the lever can do. That this mass released and this mass released, somehow this mass will do twice the work. And there's absolutely no reason to believe that, because it's already proving they do the same work. They work on each other exactly the same. They apply the same exact force to each other. So there's no way to say they, one of them can have more of anything. is it doesn't. It can't do more work. And, a ton of experiments demonstrate that you can't do more work, but whatever. People are unconvinced by ballistic pendulums and all kinds of other mechanisms that show it can't make any difference, and it doesn't make any difference. The kinetic energy can't be collected, so it's useless. Again, simple. I'm going to throw it in just because, the spaceship argument is just it's so technical in the sense that it's one of our most brilliant technical achievements is controlling all of this power and shooting things into space. And the simple fact that this thrust, they know, is just masses moving velocities. They know that's all it is. And the simple truth is, if I calculate the MV and then I calculate the MV squared, obviously I'm going to get hugely different numbers. And what number goes into the spaceship? Well, the MV number does. That's the equal and opposite reaction Newton talked about. You'll get the equal and opposite reaction to the MV. You won't get any equal and opposite reaction to this MV squared. It won't happen. And it's just a huge argument saying right there in front of your face that how can it be real energy if it can't move a spaceship? How can it be meaningful if it can't do that, if it can't obey the simple third law and create this simple function? Why would you believe it's real as any kind of energy, a standard unit? If you say there's 25,000 joules of energy, shouldn't that mean something? That you can put 25,000 joules of energy into the ship? But the fact is you can't. Ever. You can never do it better than just the momentum. That's all you'll ever put into the ship is the momentum. Not 1 joule more, not a half joule, not a Newton, not anything more than what the pressure as momentum defines it. The weight of mass moving. The momentum. Right? That seems to me a conclusive argument. Alright, so physics often talks about conservation of energy, and then they don't say kinetic energy. They just leave it ambiguous. And so, if you're like me, you could imagine momentum as being a form of energy. It's a mass moving its motion in the universe. It'd be ridiculous for me to say that doesn't have any energy. So it all kind of depends on what kind of language, you're going to use. But the clear argument is there's no way to convert, energy between objects of dissimilar mass, and conserve it, except in the form of momentum. So anytime you go from having energy and then it's in this big object and you're going to try to put all the energy into this smaller object, you can't conserve both momentum and kinetic energy, and you'll never conserve kinetic energy just because of the squared term, because of the velocity being squared. There's no way. You've just basically made it impossible, because going one way you're going to reduce the velocity dramatically, and so therefore you're not going to have the squared term. It's going to be a very small number, and you're going to lose a ton of kinetic energy going from light to heavy, and from heavy to light. If you could actually make all of the energy in the heavy thing create a very fast velocity, but you can't. So you'll never conserve, because you'll never create the high velocity from the energy in the bigger object. So the ballistic pendulum demonstrates this. Pulleys, perfectly conserve momentum. So momentum is always conserved, and kinetic energy is the one that's, in a huge number of cases, not conserved. Every case where you're changing the masses. Now, in some cases, in elastic collisions, they'll pretend that you can have momentum this way that cancels momentum that way, that somehow I could create motion, I could have a certain amount of energy, and I could make the energy go in two different ways, and they would cancel each other, and I could keep my energy going this way because this energy cancels this energy, and there's no energy used because those two cancel each other. So somehow I could create 300 momentums going this way and 100 going this way, and they could argue I could do that with just 200 going in. And I can't. because the net would just be 200. You can't make canceling momentums. So the fact is the kinetic energy fails even in these experiments because they just make up a story about what actually happens because they haven't thoroughly tested any of it. They don't have credible scientific evidence of the event they claim to be real. Okay, yeah, I can't erase that. I'll be back. Alright, so let's deal with a specific example of the spring. Okay, and so the argument being, people are claiming they have experimental evidence demonstrating this, and like I said, it's so bad that it really doesn't deserve any attention. But this is actually what they're arguing, that they could take 280 grams, okay, of pressure or energy or momentum or weight. So the weight is basically, you could argue that 280 grams at 1 mile an hour is what I could reduce that to, and say, yes, that's its capacity to do work. And then the alternative that they say they can get out of the same, so that would compress a spring a certain amount. So in gravity, that amount of mass will compress a spring a certain amount. Now they're claiming, okay, that the same exact compression would be created by a much more total momentum. So this is a momentum number, sorry, that represents, okay, we start with, let's just say it's a 1 mass. So then we have a 280 velocity, okay. And what they're going to convert that into, okay, is a heavy mass of 1900, okay, grams of pressure. So that's the momentum. And clearly, and they're going to put it in the form of something much heavier and claim it's going to go out with the same conversion of MV. And it's not, because of its gigantic weight. I mean, it has a gigantic weight. This momentum doesn't equal this momentum is a simple argument. There's no way that you could compress something with 280 grams and then move something with 1900. You can't even move it, let alone move it any specifically reasonable amount of distance. So it's, it's on its face non-conservative. They're basically saying that I can take 280 momentums, put them into a machine, and the machine will give me back 1900 momentums. So I'll have 1900 pounds of pressure, 1900 grams moving 1 mile an hour. So if I just convert it into grams moving 1 mile an hour, or 1 meter per second to create a constant velocity, I'm just saying that there's no, a comparable sameness between the two objects. There's just no way you can take something that only has 280 grams of weight and make it balance, okay, 1900 grams. It can't happen. There won't be any balance. The 1900 grams is going to be much heavier and not be able to absorb enough energy to be the same amount coming out. It's not going to weigh its weight. It's not going to be going near fast enough to weigh its weight. It's going to be way short of that 1 mile an hour because of that gigantic mass. So it's basically just making the argument somehow it's true that it takes 25 times the fuel to spin something 5 times as fast, which is ludicrous, and that something going 5 times as fast will create 25 times the work, which won't happen with a water wheel, and it won't happen with a turbine, and it won't happen with a generator, and it won't happen with anything. So they have no real experimental evidence, and they're just playing games to defend a flat earth theory. It's to deny that momentum is weight, in my opinion, is pretty much flat earth theory, because it's clear that that's exactly what momentum applies, is pressure, weight, exactly the same thing. An elephant moving 1 mile an hour into a scale is doing the same thing that it's doing when it's sitting on the scale. It's the same thing. It's just pressure being applied by a mass. And that's it. In one case, it's a constant force, so it keeps getting refueled. In the other case, it just goes in and gets pushed back out at close to the mile per hour. Alright, so I guess the only other thing to talk about is just real briefly about springs and their limitations. So the idea is the spring doesn't have a limitation going in. So it's not like you can't shoot a bullet into a spring and collect its energy. So obviously there's some velocity limitations. You can't go faster than the spring's mechanical structure can stretch and yield. But the basic idea is that yes, you can take a fast thing, a light fast thing, and a heavy slow thing, and you can basically just measure their momentums, their total net capacity to apply pressure. And but the trick is when you're releasing that energy, the problem is the light thing going fast leaves the spring while the spring is still moving fast. So the spring is going to oscillate quite a bit. And a heavy thing, though, it's going slow when it leaves the spring. So the spring is going to oscillate a lot less, so it has a lot less energy left in it. So if you want to get the most energy into something, you put a heavy object in front of the spring. You want to get the least energy out of the spring, you put something light in front of it, because it'll be impossible for most of the energy to get into the spring. So it is a liability. Springs don't give back exactly what they put in. There's always some loss, because the spring is always going to vibrate after the object leaves a little bit. It's going to oscillate. And that oscillation is just evidence that you didn't get all of the energy out of the spring. So you can't help but lose some energy in a spring rebound. And the fact is you lose more and more depending on how heavy the object is that you're pushing with the spring. All right. So I think I'll call that a video. I think I'll wait before I say anything more about the crap experiment. Let's see. And so anyway, and then I'll throw in an update on Paul Nord hasn't gotten back to me over the weekend. So I don't know, if he's going to do experiments or not, or if he's running away or what. So who knows? So that's unknown at this moment and such. So anyway, yeah, probably should have raced before I put that on the screen. Anyway, it doesn't really matter. So till the next time and such and so forth and whatnot. Yeah, so all the arguments really have already been made. That can just make subtle improvements to them. And we just need the counter argument. So we need somebody to counter argue the physics, draw us the picture, and explain how how spaceships do convert kinetic energy of their exhaust into motion. Show me. Yeah, and show me how show me where the waste is, why they can't get all the joules of the energy into the spaceship. All right, anyway, till the next time and such and so forth and whatnot.